Hello students, welcome back. In this class, we are going to start a new chapter of your class 11 physics, which is simple harmonic motion, also called as SHM. So please write down the chapter name, simple harmonic motion or SHM. Right? So does anyone know what simple harmonic motion is? You must have heard about this motion somewhere or other, right? So now let us start discussing what exactly do we mean by simple harmonic motion. The word motion, we all know about motion. We have studied in kinematics. What is rest in motion? Anyone? So what exactly motion is? Motion is when an object changes its position with respect to time, then it is said to be in motion, right? We are all familiar with this term motion. Now we want to understand what simple harmonic motion is. Before we get to understand what simple harmonic motion is, there are three kinds of motion that you should know about. First one is periodic motion. Periodic motion. Second is harmonic motion. And the third one is oscillatory motion. So these are the three kinds of motion that you should know about for understanding the meaning of simple harmonic motion. So let us start discussing all these kinds of motion one by one so that we become eligible for learning what simple harmonic motion is. So first we have periodic motion. So as the name indicates, periodic motion is any kind of motion in which the object repeats its motion after a certain period of time. For example, what are the examples of periodic motion? The example of periodic motion might be the hands of the clock. For example, if you talk about the second hand of the clock, then it repeats its motion after every 60 seconds, right? The second hand of the clock repeats its motion after every 60 seconds, so it is said to be a periodic motion. If we talk about the minute hand, it repeats its motion after every 60 minutes and therefore it is an example of a periodic motion. If you talk about the hour hand, it repeats its motion after every 12 hours, so it is an example of a periodic motion, right? And if you talk about the earth moving around the sun, revolving around the sun, then it repeats its motion after every 365 days. So it is an example of a periodic motion. So if an object repeats its motion after a certain period of time, it is called as a periodic motion. And the period of time after which the motion is repeated, that time is called as periodic time. So please first of all write down the definition of periodic motion. Please write down periodic motion heading, and under that heading please write down the definition. Periodic motion is defined as the motion that repeats itself after fixed interval of time. Full stop. This fixed interval of time is called as time period of the periodic motion. This fixed interval of time is called as time period of the periodic motion. An example you can write down: motion of hands of the clock. First example is motion of hands of the clock. So now if I ask you what is the time period of the second hand of the clock, it is 60 seconds. If I talk about the time period of the minute hand, What is the time period? 60 minutes, right? And what is the time period on the hour hand? 12 hours, right? So motion of hands of the clock is one of the examples of periodic motion. The second example is motion of planets around the sun. Motion of planets around the sun, right? Now we have studied about the periodic motion. Now what is harmonic motion? So any motion that is periodic is called as harmonic motion. So motion which is periodic in nature is called as harmonic motion. So please write down the heading harmonic motion. Harmonic motion would be just any kind of motion that is periodic, right? So we have studied about the periodic motion and the harmonic motion. Now let's come to oscillatory motion. What exactly do we mean by oscillatory motion? You must have heard about this kind of motion called as oscillatory motion. So for example, if I take one simple pendulum, we understand the definition with the help of this example. So let's say this is the ceiling, this is the thread, and this is the bob, right? A mass hanging from the string. So this is the bob, right? So now this is a simple pendulum. If you talk about, if you know what is simple pendulum, this is an example of a simple pendulum. Now suppose if I take this bob here like this, if I take this bob here and releases it, then it performs an oscillatory motion. So if we consider that there is no air resistance or resistance of any kind, then what will happen if we take this bob here and releases it, then it performs motion like this. It continues to perform motion like this, and its energy always remains conserved if there is not any kind of resistance, right? So this is an example of an oscillatory motion. So how do we define oscillatory motion? Oscillatory motion is defined as if the object, write down the definition of oscillatory motion. Please write down the definition first. Oscillatory motion is defined as the to and fro motion. The to and fro motion is defined as the to and fro motion of an object about a fixed point called mean position or equilibrium position. So you can see that this bob performs to and fro motion about this point, and this point is called as the mean position or the equilibrium position. Why? Because here all the forces on it will be balanced and the energy of it will be least, right? So this is called as equilibrium position. So it performs to and fro motion about this fixed point called as its mean position. So if any object performs to and fro motion about a mean position, then it is called as oscillatory motion, right? What could be the other example? The other example could be the oscillation or the movement of spring. Movement of spring, if you talk about, if you take, let's say there is a spring which is fixed to one end, and if you elongate that spring, then it compresses, elongates. So it performs to and fro motion about its mean position or the equilibrium position. So it is an example of a oscillatory motion. So please write down the examples. First example is oscillation of simple pendulum. You can draw this diagram if you want for a reference. So first example is oscillation of simple pendulum. Next example is movement of spring. Third example might be the swinging of the string. आप लोगों ने झूला होगा जिसमें यहाँ पे एक इंसान बैठता है and फिर वो ऐसे झूला झूलता है. So swinging of the string is another example of oscillatory motion. So I hope you are now clear with these three terms: periodic motion, harmonic motion, and oscillatory motion. Right? now we are all prepared to learn about the simple harmonic motion. So now let us discuss what do we mean by simple harmonic motion. Before coming to learning about the simple harmonic motion, let us discuss one more thing which we should know about the oscillatory motion, and that thing is the condition for oscillatory motion. What is the condition for performing the oscillatory motion? So you need to remember that the condition for performing the oscillatory motion is A is directly proportional to minus of x to the power 2n plus 1. This is the condition for performing the oscillatory motion. If this condition is satisfied, only then the particle can execute oscillatory motion, otherwise it cannot perform the oscillatory motion. So this condition means that acceleration of the particle should be proportional to its displacement should be proportional to the odd power of the displacement from its mean position, and negative sign indicates that the acceleration is always towards its mean position. For example, if we look at this diagram, this is a simple pendulum executing the oscillatory motion, right? So now if we draw the free body diagram of bob here, so there will be a force mg in the downward direction like this, right? Let's say if this angle is theta, then suppose if I extend this line, there will be tension in this string. Let's say the tension is T, and this angle will be theta, right? These two are parallel lines, so these are corresponding angles. So this angle will be theta. So now if we take the component of mg, this component of mg will be equal to mg cos theta, and this component, there will be a component that will act in this direction, which will be equal to mg sin theta, right? So now when bob is at this position, this component of mg tries to bring the bob towards its mean position, right? And similarly, if we talk about here, there will be a component of mg which is again mg sin theta, which tries to bring the bob towards its mean position. So here acceleration is g sin theta, here also acceleration is g sin theta. So there is an acceleration which is always directed towards the mean position of the particle. See, this acceleration and acceleration at every point will be directed towards the mean position. So that is what this condition is saying, that minus sign indicates that acceleration should always be towards the mean position, and this thing says that acceleration should be proportional to some odd power of the displacement from its mean position. This condition will become more clear as we further proceed, and we will discuss this equation again with the help of spring mass system, right? So for now you need to remember that the condition for oscillatory motion is A is directly proportional to odd power of displacement from its mean position, and there is negative sign which shows that acceleration is directed towards the mean position. So you can write down this condition. Please write condition for oscillatory motion. Write down condition for oscillatory motion. So please under this heading write for oscillatory motion, A is directly proportional to minus x to the power 2n plus 1. So now write down the meaning of this condition. Thus for performing the oscillatory motion, the acceleration of the particle should be directly proportional to the odd power of its displacement, should be directly proportional to the odd power of its displacement from the mean position, and is always directed towards the mean position, and is always directed towards the mean position, and is always directed the mean position. So now with this knowledge, we are ready to learn about simple harmonic motion. So now let us start discussing about simple harmonic motion. So, as the name indicates now, let us understand each word of simple harmonic motion one by one. So here what simple means? Simple means a simple motion. That means motion in a straight line. Motion in a straight line is the simplest kind of motion. Motion in a straight line. So simple means in a straight line. Right? Harmonic. What is harmonic motion? Just now we studied harmonic motion is any kind of motion that is periodic. So harmonic here means periodic motion. Right? And motion is motion. So apart from these two conditions, there is one more condition, which is that it should be oscillatory. So there is one more condition, that it should be oscillatory, and SHM or simple harmonic motion is the simplest case of oscillatory motion. For oscillatory motion, the condition is A is directly proportional to minus x to the power 2n plus 1, and this is simplest when n is equal to 0. When n is equal to 0, then A is directly proportional to minus x. Oscillatory, so simplest case. And for this, the condition is A is directly proportional to minus x. So these are the three conditions for oscillatory motion. Any motion will be called as simple harmonic motion only if it meets all these three conditions. If any of these three conditions fail, then motion will not be called as simple harmonic motion, right? So on the basis of these conditions, we can define simple harmonic motion as, please write down the definition. Please write down the definition of simple harmonic motion. Simple harmonic motion is defined as a periodic motion of a particle along a straight line such that its acceleration is always directed towards a fixed point called mean position or equilibrium position. In that line and is proportional to its distance from that point. So basically, if you read the definition again, you will find that this definition has been framed on the basis of these three conditions. What simple harmonic motion is? Simple harmonic motion is defined as a periodic motion which is along a straight line and in which the acceleration of the particle is directly proportional to its displacement from the mean position, and negative sign indicates that the acceleration is always directed towards the mean position. अब हम इस डेफिनेशन को एग्जांपल के साथ समझते हैं, राइट? एंड उसके साथ हमें सिंपल हार्मोनिक मोशन और ज्यादा क्लियर होगा, राइट? सो प्लीज राइट डाउन एग्जांपल ऑफ सिंपल हार्मोनिक मोशन. Example of simple harmonic motion. So now we are going to discuss one example of simple harmonic motion. Let's say this is the wall is a surface. So this is a wall, fixed wall, immovable. So this is a wall which is fixed and this is a surface which is frictionless. I am assuming that the surface is frictionless, right? Okay, let me draw it again. Right? So this is a frictionless surface. Clear? Now, let's say there is a spring whose one end is fixed with this wall. So this is the spring which is fixed to this wall, and the other end of the spring is attached with a mass M. So this is called as spring mass system, right? Right now this system is in equilibrium position, means that everything is at rest and this spring and mass are also at rest, and right now there is no force, or we can say that all the forces on it are balanced, right? So this is in a rest condition, or we can say equilibrium condition, right? Now what happens is I select this mass, or I hold this mass and I try to bring it in this direction, and I try to bring it in the positive x direction along I cap. Then what happen? Then what will happen? This spring will get elongated, right? This spring will get elongated. I am drawing that picture there, right? So if I draw a line like this, this is equilibrium position or mean position. Equilibrium position or mean position. So if I ask you when a particle is said to be in equilibrium, when all the forces are balanced on it, right? Then the particle is said to be in equilibrium, and this position is the position of equilibrium. Now I am stretching this mass in the positive x direction, as a result of which the spring gets elongated, right? So let's say the mass has finally come here. This is mass m, and the spring has got elongated like this, right? So now what will happen, because this string has got elongated, so there is a property of the spring. What will happen? A restoring force will come into picture, which will try to restore the original position or the equilibrium position of the block, right? So there will be one restoring force, let's say F, in the spring, which tries to restore the original equilibrium position or the original position of the spring or the mass, right, of the spring actually, okay? This restoring force F, what it tries to maintain the equilibrium position of the spring, right? When the energy of the spring is least or all the forces on it are balanced, then the spring is said to be in equilibrium. So there will be a force in this direction, or we can say that the acceleration of the spring will be in this direction, right? And if you see, experiment says that this restoring force F is proportional to its displacement from the mean position. That means if right now this distance or the distance by which the spring is stretched is x, then force will be directly proportional to x. The more you stretch the spring, the more will be the restoring force acting on it. right? And this restoring force will try to restore the equilibrium position of the spring. So there will be a force in this direction. So now you can see, according to the third condition of the simple harmonic motion, which was that acceleration should be proportional to minus of x. So you can see that due to this restoring force, an acceleration is coming into picture which is acting towards the mean position of the particle, right? So in this case, A is directly proportional to minus x. Here A is directly proportional to minus x. Why minus? Because it is acting towards the mean position, and restoring force is proportional to its displacement from the mean position. The more you stretch the spring, the more restoring force acts. Right? So what will happen? This surface is frictionless. So now with the acceleration in the backward direction, what will happen? This spring, now if I release this mass, then what will happen? This mass will come like this. Due to this restoring force, the spring will try to restore its original position and it will compress itself like this. So now with this acceleration, if the spring and mass comes in the backward direction, they will not stop here. Instead, the spring will be compressed like this. So again I am drawing a picture which is compressible, or the compressive picture of the spring. Right? This is the equilibrium position I am drawing, and now the mass M will be somewhat here. So this is mass M and the spring is compressed. So here the spring is compressed. Now what will happen? Again there will be a restoring force in the spring which tries to restore the equilibrium position. So now if spring wants to restore its equilibrium position, the restoring force will act in the forward direction. Okay? The restoring force will act in the forward direction, which will push the mass M in the forward direction, right? As a result of which the mass M will move forward. So there is acceleration in this direction, right? So again, restoring force is proportional to its displacement from the mean position. If this distance is x, then F will be proportional to x. And again you can see that because restoring force in the positive direction, so acceleration will also be in the positive direction, and this acceleration is again directed towards the mean position of the spring, or the equilibrium position of the spring. So now what will happen? This spring mass system will continue to oscillate like this. It will elongate the spring, then the spring will be compressed, then again it will be elongated, again it will be compressed, and it will go on forever, because we have assumed that the surface is frictionless, so there is no resistance of any kind, so there will be no loss of energy, right? So the energy of the system will remain conserved once we have, because we have done the work on the system by taking this mass here. So this work done will be stored in the form of energy of the system. So due to this energy, it will again convert into the potential energy, kinetic energy, potential energy, kinetic energy. So in this way, the energy gets converted, and this system will elongate, compress, and it will go on forever, right? So you can see that this motion is in a straight line, right? This motion is in a straight line. So first condition is satisfied, the simple harmonic motion. So the motion is simple, the motion is in a straight line, and what is harmonic? It should be periodic. So after every period of time, you will see, after a certain period of time, after a certain time period, you will find the block at this position, right? So the motion is periodic, so it is harmonic, and the third condition is that it should be oscillatory. So again, A is directly proportional to minus x, because F is directly proportional to minus x, so A is also directly proportional to minus x. The restoring force is proportional to its distance from the mean position, and acceleration is always directed towards the mean position. So all the three conditions are satisfied, and therefore this example is an example of a simple harmonic motion. I hope this is clear to everyone. So please now draw this diagram and write down the theory that I am going to give you now. So please pause the video and draw this diagram, and then we shall move forward, right? I hope you have drawn the diagram. Now after drawing this diagram, please write, thus we see that the force exerted by the spring, in the bracket you can write spring force, because restoring force is due to the spring, so it is also called as spring force, right? So the force exerted by the spring is always towards the equilibrium position. The force is always directed towards the equilibrium position, full stop. If the displacement of the spring from the equilibrium position is x, if the displacement of the spring from the equilibrium position is x, full stop, then restoring force will be F is equal to minus kx. So this will be the restoring force F. Then restoring force will be F is equal to minus kx. Full stop. Here K is called as spring constant. Here K is called as spring constant or force constant. Spring constant or force constant. So I hope the meaning of simple harmonic motion is clear to you. And what do we mean by periodic motion, harmonic motion, oscillatory motion? What is the condition for oscillatory motion? And then on the basis of those motion, how do we define simple harmonic motion? What are the conditions for simple harmonic motion? And this example of simple harmonic motion. So now let us stop in this class, and in the next class we'll learn some concepts related to the simple harmonic motion. So goodbye for now. Take care. Keep studying. Goodbye.